Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at infrared spectroscopy. We're going to talk about what infrared spectroscopy actually is, how it works, and the use of IR spectra to determine the functional groups and bond types present in organic compounds. Before we talk in detail about infrared spectroscopy, there are a few essential ideas you need to be comfortable with. A covalent bond forms when two atoms share a pair of electrons. The atoms are held close together due to the attraction of their positively charged nuclei to the shared pair of electrons. Organic molecules contain carbon and usually hydrogen and oxygen atoms. The electromagnetic spectrum refers to a complete range of wavelengths of electromagnetic radiation. The infrared or IR part of the spectrum describes electromagnetic waves with a wavelength between 780 nanometers and 1 millimeter. The shorter the wavelength of an electromagnetic wave, the higher its frequency and its energy. Recap done? Let's go! Infrared spectroscopy is a technique used to identify the bond types and functional groups present in organic molecules. The technique centers around the idea that covalent bonds can absorb specific amounts of energy to vibrate in certain ways. There are two main ways a covalent bond can vibrate. The bond can stretch back and forth in what are called stretching vibrations, and they can bend up and down in what are called bending vibrations. To make a bond vibrate in either of these ways, the electrons in it must absorb a specific amount of energy. For most bonds in organic molecules, this energy can be found in waves from the IR region of the electromagnetic spectrum. Meaning if a specific wave of IR radiation is shone at a sample that provides just the right amount of energy needed to vibrate a particular bond in it, the bond in the sample will absorb this energy from the wave and begin to vibrate. Different bond types require different amounts of energy to vibrate, meaning they can each absorb different wavelengths of IR radiation. By bombarding a sample with a range of IR waves, all with different wavelengths, the wavelengths that pass through the sample can be detected, and from this, the wavelengths that must have been absorbed by bonds in the sample can be found. This is the background of IR spectroscopy. A complete range of IR waves are shone at a sample, and the waves that pass through it or are transmitted are recorded. Wavelengths of IR that aren't detected or are detected at a very low intensity must have been absorbed by bonds in the sample. As we know different bond types absorb specific wavelengths of radiation, we can use the wavelengths absorbed by a sample to identify the types of bond that must be present in it. Wavelengths are used to distinguish between different infrared waves, however these can be very small values, meaning wave numbers are used instead to make things a little easier. A wave number is just 1 divided by wavelength, with units of centimeter to the -1. The bigger the wave number, the smaller the wavelength and higher the energy of the wave. Tables are produced that show the wave number range commonly absorbed by particular bonds. As the exact environment of a bond will change its energy slightly, the same bond type in different molecules will absorb slightly different waves with different wave numbers, meaning a range of values is given in such tables. For example, as can be seen in the table shown, a carbon-oxygen double bond will usually absorb IR waves that have a wave number between 1680 and 1750 centimeters to the -1. Meaning if a range of IR wave numbers are shone through a sample of ethanol in an IR machine, there will be an absorption at around the 1680 to 1750 range for the double oxygen bond in the ethanol. However, there are other bonds in the ethanol as well, meaning other waves will also be absorbed. To help show all the absorbances that occur, a graph called a spectra is produced. When a sample has a range of IR wavelengths shone at it, a detector records the wavelengths of IR that pass through the sample. The waves detected are not absorbed by the sample. They were fully transmitted and have a transmittance of around 100%. The wave numbers of the waves shone at the sample and their corresponding transmittance are plotted on graphs called spectras, with transmittance on the y-axis and wave number on the x-axis. Any wave numbers that have a low transmittance haven't passed through the sample easily and must have been absorbed by bonds within it. For example, the molecules ethanol, ethanal, and ethanoic acid all have slightly different IR spectras, as they contain different combinations of bond types, with the main absorbances being around the 3000 mark and the 1650 mark. The big absorbances around the 3000 wave number mark are due to the presence of an OH group in the ethanol and ethanoic acid molecules, and the absorbances around the 1650 mark are for the carbon-oxygen double bond in ethanal and ethanoic acid. Below wave numbers of 1500, the absorptions of waves are associated with vibrations and motion of whole molecules in a sample, meaning they are very complicated to analyze. The combination of all absorbances in this region are unique to a particular compound, however, and as a result, it's referred to as the fingerprint region of a spectra. Due to its complexity, it isn't usually analysed in detail at this level. It can be used as a quick and easy way to identify a compound, as no two compounds will have the exact same fingerprint region on their IR spectra. OH bond stretches have very characteristic absorbances in IR spectras and are described as broad, meaning they cover a large range of wave numbers on a spectra, given a large curve. The reason for this is because the oxygen and hydrogen atoms in an OH bond are able to form hydrogen bonds with other oxygen and hydrogen atoms from OH groups in neighbouring molecules. When these hydrogen bonds form, the energies of electrons in the OH bonds change slightly, meaning a different amount of energy is now needed to make the bonds vibrate. As a result, the electrons in the bond will absorb a slightly different wavelength of IR radiation. As hydrogen bonds are constantly being formed and broken, and they can form at different angles and distances, lots of OH bonds in a sample will absorb slightly different energies, meaning a range of wave numbers around 3000 gets absorbed by the sample, shown as a broad absorption on the spectra. So, to summarise, infrared spectroscopy is a technique used to analyse the bond types and functional groups present in organic molecules. Covalent bonds can absorb specific amounts of energy to vibrate in certain ways, and different bond types absorb different amounts of energy to do this. For most organic molecules, the bonds in them can be made to vibrate using energy found from the infrared region of the electromagnetic spectrum. This means if a specific wave of IR radiation is shone at a sample, the corresponding bond type in the sample can start to vibrate by absorbing the energy from the wave. By bombarding a sample with a complete range of IR waves, the wavelengths of IR that get absorbed by the sample can be analysed and the types of bond in the molecule found. Wavelengths are used to distinguish between different IR waves. However, wavelengths are very small, meaning wave numbers are used instead, to make things easier. A wave number is just 1 divided by wavelength, with units of centimetre to the -1. The bigger the wave number, the smaller the wavelength, and higher the energy of the wave. Tables are produced that show the range of possible wave numbers a particular bond type is likely to absorb. The same bond type in different molecules will absorb slightly different wave numbers, which is why a range of values is always given in such tables. In infrared spectroscopy, spectra are produced that show the waves that pass through a sample. This is called transmittance. Any waves or wave numbers that weren't transmitted must have been absorbed by bonds in the sample. These wave numbers absorbed can be compared to a data table, and the corresponding bond types can be determined. Below wave numbers of 1500, the absorptions of IR waves are associated with vibrations and motion of whole molecules, meaning they are very complicated to analyze. The combination of all absorbances and the shape of this region is, however, unique to a particular molecule, meaning it is referred to as the fingerprint region. Due to its complexity, it isn't analysed in detail at this level and is instead just used to quickly identify given substances. OH bond stretches are described as broad and cover a wider range of wave numbers on a spectra than you would otherwise expect. This is due to hydrogen bonding arising between oxygen and hydrogen atoms from different OH groups in neighbouring molecules. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.